Alrighty, so we are talking about L'Hopital's rule. This is in section 4.4, and as I mentioned before, I'm going to do this in two parts, and so this is L'Hopital's rule. We did a couple of examples in our problem session the other day. Well, today, I guess. Talking about how to use L'Hopital's rule. And so I'll do another example of that here in a little bit, but I do want to just go ahead and jump right into the proof. All right, and as I mentioned, I'm going to focus on the proof at 0. And so we know L'Hopital's rule stated, says basically that if f and g have if f and g, I'm going to try to summarize this a little bit better. I don't want to write it word for word out of the book. If f and g go from I minus a into r, a is some real number, right? Or f and g are defined on some infinite interval. I'll call it b to infinity. Let's just say r. Let's just say the real line. It's defined on the whole real line. Okay, and this is kind of the segue here. So if f is defined here or that, and if the limit as x approaches a, right, x and I, remember our symbols here, of f is equal to the limit as x approaches a, x and I of g of x, and that's equal to 0 or plus or minus infinity. Okay, and they don't, and plus or minus infinity means that one of these could be plus infinity and one of these could be minus infinity. So this equal sign is kind of a, yes, it's equal, but not exactly all the time, right? Then if the limit as x approaches a, x and I of f prime over x, sorry, f prime of x over g prime of x exists, then the limit of x goes to a of x and I of f over g equals that limit. Okay, and you can only do this for 0 over 0 or plus or minus infinity over infinity, plus or minus infinity. Okay, if you have a ratio and your limit is 1 over 7, you can't use L'Hopital's rule. It's not true. Okay, so let's jump into the proof. For the proof, I am going to focus on we're going to do the basic case. And the basic case is a is a real number, not plus or minus infinity. And the limit as x approaches a, x and I of f is equal to the limit as x approaches a, x and I of g, and that limit is 0. So we're doing the 0 over 0 case. All right, so again, if you come back to this definition, right, for this guy, we could have had this a actually be infinity. Okay, you could take the limit as x goes to infinity also. That's why I rewrote this over here. So a is in, technically, I guess I should say that A is an extended real number, right? So how do we write that? A is an extended real number. Like that, right? So if A is a real number, then you can write it like this. If A is an extended real number, then you would have it like this, okay? So anyway, I hope that's not too confusing, but trying to get there. So what I'm saying is that I'm doing the most basic case here, and the proof process is the same regardless. And so anyway, so what we're going to do is choose x sub k in I such that x sub k converges to A as k goes to infinity. All right. Further, I want I could, right, choose x sub k such that x sub k is always bigger than A, or x sub k is always less than A for all k. All right, I could just pick the ones. I could take a subsequence, right? If x sub k converges to A, I can just take a subsequence of numbers that are all bigger than A, or the infinite side that's all less than A. One of the two is going to happen. I can do this at least one direction. And so the reason I could do that, I'm not going to necessarily write it, but I could do that. So I really only need to focus the proof on one-sided limits theoretically, right? So I'm not going to pick which side I'm going to do. I'm just going to say that I'm not worried about the one-sided limits. Okay, so I'm looking at it as an overall thing. I could simplify this down even further by making it one-sided limits if I wanted to, and that would still be okay. So instead of having to do the one-sided limits each single time, I'm just going to look at the overall limit. Okay, so there you go. That's the idea. Okay, so we're going to use sequential characterization. We haven't done that for a little while, right? Theorem 317. That's going to be kind of the method of how we get through this. Okay, so we're going to assume that by definition that definition, sorry, of the this is not good. Okay, so anyhow, one of the hypotheses here that I did not state, because we're used to just throwing this out here, we actually need in this hypothesis here that g of x is not 0 and g prime of x is not 0 on I minus a. All right, we need those both so that we can talk about the ratios. And again, the only time this would really matter is that if I have this. All right, so I'm recognizing that I forgot that hypothesis, and so because I need it right here, since g prime of x is not 0 on I minus a, then the mean value theorem, the basic mean value theorem, gives us that g of x minus g of y cannot be 0 either for x not equal to y in I minus a. Now, why is that the case? Remember what the mean value theorem states. The mean value theorem says that for a function, g prime of c equals g of b minus g of a over b minus a, right? And so how would that be 0? That could only be that could only be 0 if these two were equal to each other in the numerator. And so if this is not 0, means that the numerator is not 0. Right? And that was true for endpoints A and B, but we're saying this is true for any x and y that just makes a small interval x to y. Okay, so we're just doing it in general instead of calling them A and B that represent kind of endpoints. These are for any x's and y's that are not equal to each other in this interval. Okay, so we have this ratio that I can write. All right, so here's the idea. If I take an x sub k in I minus a and a y in I minus a, x sub k not equal to y, then I can look at f of x sub k minus f of y over g of x sub k minus g of y. And so this has to be equal to some f prime of ck over g prime of ck by the generalized mean value theorem. And this is true for every k in the natural numbers because x sub k is a sequence. So if I take one of them, I can do this, and so for any of them, I get a sequence of ck's also. All right? And so now, since we know that f and g have limits at a, we can extend f and g to the full interval I now by defining f of a equal to 0 and g of a equal to 0. So technically these are extensions, right? So these are not the same function. They are equal, right? F equals f hat and g equals g hat on I minus a. But they're continuous extensions, all right? So we're not doing uniform continuity, but it's the same idea. We're extending them to make sure that f and g are continuous. So f hat and g hat are continuous on all of I now, thanks to that. And so this mean value theorem deals with the hat guys as well. All right, so your textbook doesn't introduce this hat notation, but I'm going to. And so by extension, then, what we have, f hat of xk minus f hat at a over g hat of xk minus g hat at a must be equal to some kind of f prime of ck and g prime of ck. All right, so these are maybe hat primes, whatever, but same idea. Okay, so don't worry about the notation, but my point is that you have this, and because these are equal, right? F equals f hat on I minus a, which means that all these points that are not a, I don't really need the hat, right? I don't really need the hat at all. And so that's why I kind of jump back and forth with the notation. But this is derivative, and the derivative is the same because the functions are the same. These guys are the same function. The derivative exists everywhere except possibly at a, but I don't care about a because ck is not equal to a, right? And it's not equal to xk either because it's in between here. Okay, so here's the deal. Let's I'm going to cut this here and take it. Oops, I don't want to cut both of them. Well, apparently I'm going to. Maybe I can get this and copy that. All right, so that's the last line we just had. So here's the idea. Okay, so since we defined f of a equal to 0 and g hat of a equal to 0, then if you take a look at f of x sub k over g of x sub k, that's the same as f of x sub k minus f hat of a and g of x sub k minus g hat of a, because those are 0. But then that was equal to f prime of ck over g prime of ck by the generalized mean value theorem. That's where this came from, right? So I have now a relationship between the ratio of the f's, f and g, and the ratio of the derivatives, okay? And so now I'm going to take the limit of both sides. So limit as k goes to infinity of f of xk over g of xk has to be the limit as x approaches, as k approaches infinity, as k approaches infinity of f prime of ck over g prime of ck, obviously, because if it exists. If they exist, they're equal, okay? And so now, notice this. Since x sub k was defined to go to a as k goes to infinity, and by the mean value theorem, okay, the general one, but it doesn't really matter, where is ck located, right? ck is between xk and a for every k. So where does ck go? ck has to go to a as k goes to infinity by the squeeze theorem. All right, so I don't have any qualities because technically, right, x sub k might be bigger than a, so then ck is in between and x sub k is on the right, or x sub k might be less than a, so ck is in between and xk is on the left. It doesn't matter, right? The squeeze theorem gives us both sides. So ck is going to a, which means by where do we have, what do we have here? Okay, yeah. So by sequential characterization, the limit as k goes to infinity, okay, of f of x sub k over g of x sub k, okay, sorry, prime, these guys are primes, right? This limit, which we know exists, that was part of the hypothesis, this limit exists, okay, is equal to the limit as xk, these are, oops, sorry, these are ck's, right? And so since ck is going to a, this has to be the same as the limit as x approaches a of f prime of x over g prime of x. And we know this limit exists, so this limit exists, but this limit's equal to this limit. And once again, by sequential characterization again, limit as as k goes to infinity of f of xk over g of xk has to be the limit as x approaches a of f of x over g of x. All right, and so this guy, this was assumed to exist. This equals this equals that, and that equals that, right? So basically we have kind of one, this was given to exist, that equals this, which equals this from above, which has to equal that by sequential characterization, all right? And so 1 equals 4, and so those two are equal to each other, and that's what I wanted to prove, okay? All of the other theorem proofs, all of the other versions, when you're taking the limit to infinity, when you have a limit of infinity over infinity, plus or minus, the algebra just gets horrible, right? But it's not any different in the type of proof that you do. And it's the same basic idea. You still use the generalized mean value theorem, okay? So you're not going to have to repeat that kind of proof. That's very, very technical, and I'm not going to ask you guys to do that, right? I told you that I'm really just interested in you being able to handle L'Hopital's rule, okay? And so I'm going to do a couple more examples here as far as what I would expect you to be able to do for homework from the L'Hopital's part, right? I'll give you the other part for Taylor, but from the L'Hopital's part, all right, just take a look at 4.4.5, that problem there, all right? And that's probably the only one you really have to worry about, all right, because that gives you lots of practice, okay? So all parts, obviously, A through H, all parts there, all right? So let me give you an example of how we handle L'Hopital's rule, limit as x approaches 0 of the sine of x squared all over 4x. If you plug in 0, you get 0 over 0. And so we use L'Hopital's rule. All right, and so what that means is we're going to take the top, and you need to remember, you always need to justify. So even in your thing here. Let's just say by L'Hopital, we take the limit of the derivative of the top, cosine of x squared times 2x, right, over the derivative of the bottom, which is 4. And so the numerator becomes 0 and the bottom becomes 4, and you get 0. All right, and so I'm done. Simple enough. Now, what happens if it's not quite that obvious? All right, obviously there's a lot more complex scenarios than this. Excuse me. Take the limit, for example, of 1 over x times the natural log of x. All right, let me show you something that's a little bit more. Do the limit as x goes to 0 from the right of x times natural log of x. All right, so obviously as x goes to 0, and then the natural log, remember, as you approach 0 from the right, this goes to negative infinity. So I get 0 times infinity or 0 times negative infinity. That's indeterminate, and so I can't do that. But I can't apply L'Hopital's rule either because it's not in the right format. So first, by algebra, all right, you don't have to say by algebra, I'm just showing you where it comes from. I'm going to rewrite this as the limit as x goes to 0 from the right of the natural log of x over 1 over x. Multiplying by x is the same as dividing by 1 over x, and now this becomes negative infinity over infinity, and so now I can use it. Now I can use L'Hopital's rule because I'm in the right form. And so by L'Hopital, I'm going to take the derivative of the top and the derivative of the bottom. Derivative of the top is 1 over x. Derivative of the bottom is negative 1 over x squared. I'm going to rewrite that algebraically. All right. I'm going to get negative x squared over x, and so that reduces to negative x, which gives me a 0. Okay, so obviously both of these had a limit of 0 at the end. That's not always going to be the case. The example we did the other day had a limit of e, so, right? But that's the deal, and that's L'Hopital's rule. Relatively straightforward. Don't worry so much about the proof, even though I wanted you to see it. It's more important that you're able to work through the progress and the problems. Go back and take a look at our problem session from the 2nd of April if you want to see a couple of other examples for L'Hopital's rule again. Okay? Thanks. See ya.